actually very reluctant to give a talk at this workshop. And I think it's actually not only appropriate but right for him to actually give the closing presentation. And that's not just because of his outstanding record of research in the subject of the workshop, but also because David's been the person who has been responsible really for putting the whole programme together and for ensuring its successful execution. So, David Balding.
Thanks very much, Norman. Yes, I was trying to get my PhD student Christ Steele to come along and give this talk, because a lot of it's about work with him, but he's moved on to a different field now and wanted to concentrate on that and not come here. I was very upset when James told me I was being hypocritical for telling people to finish up on time, because he said I never do. and I thought, I thought I was pretty good, but actually on reflection I probably am not very good, and I'm probably not going to be very good today either. But so I've got quite a few things to say, but I'll just go over at a fairly high level, and if people want to discuss further, then we can do that over lunch or later. Or so. You've already seen many, oops, that's the wrong button, discussions of different software algorithms for analyzing complex DNA profiles. So we've got one as well that's been around for a few years now as a discrete model, just modeling presence, absence of alleles, but now for the last year we've had a sort of peak height version. And there's some what's the word, coming together of different of different models here. So many people are using gamma models for the peak heights, and the degradation models are pretty common. Our starter model is a linear, that the starter peak height is or the fraction of starter is a linear function of the longest uninterrupted sequence, following research by others. One thing that's maybe a little bit different about our model, I haven't seen anybody model drop-in in the same way. So the idea of drop-in is that there's this, highly fragmented DNA which is everywhere in the environment, including airborne, and so there is a sort of literally, the idea of DNA alleles raining down upon us in more or less random, because the DNA is so fragmented, and so we have an additional DNA dose. So in other words, there's a certain amount we measure the amount of DNA in RFU, which is the unit that's used for the peak heights on the electropherogram. So a certain amount of DNA, we just say, comes as drop-in, which is modeled not as the whole genome of an individual, but just like a raining down of DNA in proportion to the population frequency. So if it's rare in the population, then it's also less likely to be a drop-in allele, but also with degradation to reflect the fact that drop-ins tend to be biased towards the shorter fragment lengths. And there's some disagreement about how to estimate model parameters. We used maximum penalized likelihood, so the penalties can be thought of as Bayesian priors, but we don't integrate them out. You can argue about this. Some models do integrate and some don't. And I'm just going to tell you a little bit about some properties, trying to emphasize different things from what others have already emphasized. I guess one other thing to say is it's open source, and the code's available. So I'm going to show you a little bit of results of some lab-based validation experiments, and I'm very proud of this. This is the first ever lab experiment that I was kind of in charge of. Chris, my PhD student, did the lab work, but he and I together had to design the experiment. And of course, it's one of statisticians' professional duties is to criticize scientists for not designing their experiments properly. But then when you come to design an experiment yourself, you realize it's actually quite hard to think in advance of all the relevant factors, and we didn't design the... I think one thing we'd say in retrospect is that this 250 was too big in terms of sort of optimally getting at what the sort of features that we wanted. But as you can see, we did some 1, 2, and 3 contributors, and the 2 and 3, there was an equal and an unequal, and the unequal for the 2 contributors was highly unequal, and also between the top and the bottom contributor here, but there was an intermediate one for the 3 contributors, so the problem was not so bad. And we also did 2, 3, and 4 replicates of each of these in order to investigate the value of replication that I'll come to in a moment. Here, so with the checking that we did with those known source lab-based profiles, some of the things we did are similar to what other people have done, so I won't go over that, just show you a few little different things. This one I thought was quite interesting. This is the two contributor profile where we're varying the dose, the DNA dose of contributor 2. So over the left here is, right at the left-hand axis, is there's 60 picograms from contributor 2, which is a pretty low amount, not super low, but the 0 on this log scale is where the contributor 2 equals contributor 1, which is 600. This is RFU, not picograms. But anyways, it's some measure of the amount of DNA. And so these curves correspond to the probability assigned to different genotypes. And this dotted one here is the correct genotype. And this is the peak height model on the left and the discrete model on the right. And the genotypes of the 2 contributors here had 1 allele in common, so there were 3 distinct alleles, and therefore there are 12 possible combinations for, taking order into account for the 2 genotypes of the 2 contributors. And so the discrete model basically all the way across assigned probability 1/12 to those 12 genotypes and 0 to everything else with a little bit of noise near the origin. And the peak height model had this slightly unusual behavior, but as you, it's able to get the correct genotype with 100% provided the amount of DNA for contributor 1 is not too low. Obviously this is a very low amount of DNA here going down to 60 RFU peak height. But also when contributor 1 equals contributor 2, then you get, that you can't distinguish the genotypes. And so then you're down to this situation. But instead of 12, because you can distinguish the major from the minor, there's only 4 different combinations here. So that peak is 4 different genotypes are allocated 0.25 probability. And so that just seemed to behave quite nicely and according to expectations and kind of encouraged us that the model behaved well. There was going to be a question there. Is that still a question, or did I answer it? No. Good. Okay. We then went on to have a look at the behavior of the peak height model versus the discrete model on the same samples, and we've seen a few of these here. I've just got a few different a point that I think others have since or about the same time published, but I don't think anybody's mentioned this week, is that so the y equals x line here means that the likelihood ratio coming out of the peak height model would be the same as from the discrete model, and instead of likelihood ratio on the axis, what this is expressing the likelihood ratio as a fraction of the maximum possible. The maximum possible is actually slightly more complicated that because we did it on a log scale, but the maximum possible is the likelihood ratio you would get from seeing a single, a perfect clean single contributor DNA profile, so basically where you can infer the genotype exactly. But the interesting observation we thought would seem a little bit surprising was that 2 equal contributors with very low amounts of DNA each, there's no particular advantage to the peak height model. When there are unequal contributors, the circles here correspond to the major being the queried contributor for the likelihood ratio, and the crosses correspond to the minor being the queried contributor. So then there is a pretty big gain. The peak height value gives you more information. The alleged contributor is always a contributor in these ones here. So higher likelihood ratio is always better for these ones here. We did see again that there were some cases where the discrete model actually gave a likelihood ratio less than 1 because it's not efficient use of information, but the peak height model here for these 2 contributor ones was still greater than 1. Well, the reason, so this is a little bit surprising because with equal contributors, the peaks for a single allele are all about the same heights typically, except for the noise, but there should be some information in higher peaks corresponding to homozygotes or to two copies of the same allele, but it seemed like the extra information coming from that was negated by other factors, or it didn't show out in the end. Were you about to say something? Or
I just had a question.
Yeah. Go on.
For the unequal ones, I take it you just looked at the minor and didn't try to use an assumed?
Well, actually, we did both, but I think these here we treated the other as the unknown for the. But anyway, it turns out that that information about two copies of an allele doesn't really come through in terms of stronger likelihood ratio, and possibly because there's extra noise here. Yes.
Big comment. I think because you don't have that many contributors in here, you have 1, 2, and 3 person mixed.
Yes.
Then you get a lot of information just from seeing an allele and not seeing an allele.
Yes.
So therefore, I think it's not too weird that the discrete and the peak height give roughly the same information. So unless you have very little DNA, maybe.
I guess, but if there are 3 alleles, so you know one of them is duplicated, you'd kind of expect that you could pick out the one that's duplicated with a higher peak, and you would get that would give you more information, but it seems to be not a lot. And in fact, I've got some examples here where a kind of eyeballing of the EPG gives you the wrong answer, and because this is the truth known situation here. So looking at these, you might think these 2 taller peaks go together and the 2 shorter peaks go together, but they don't. It's wrong in this case because the peak height variability is more than you expect with these relatively low amounts of DNA. And similarly here, the 14 peak is much bigger, and so you might think that's the one that's duplicated because there's only 3 peaks, so one of them has to be duplicated. But in fact, it's not. It's the 11 is the one that's duplicated. So this is just showing that there is a fair bit of, these were picked out to be kind of difficult ones. There's a fair bit of variation in peak heights, even in this pretty controlled situation. And so there isn't a huge amount of information in the peak heights. And these ones, you don't exactly get the wrong answer, but it's difficult. For example, this is a stutter peak, but this is allelic, and by eye, they look pretty much the same. So it's just, they're saying that it is difficult to get the information here.
It's hard we can't read the y-axis. Can you just say what the range of peak heights is?
Oh, yes, okay. I can't either. So this is going up to 1400 RFU. So those low peaks, this low peak here is about over 200, 200 or 300. And then this is going up to 1000. But this one is much lower. This is going up to 150. So these are very low peaks here. And this one, so the 2 that were the most extreme are pretty low peaks, but all those peaks are at least above 50 RFU, which is a pretty conventional threshold in the UK, a fairly conservative threshold. And then with 3 contributors, again, the 3 equal contributors are in red, and again, there's not much benefit. Those points are not much to the right of the line, indicating there's not much benefit to the peak height model over the discrete model. But when we had the unequal case, now these different symbols are trying to indicate whether it's the major or the middle or the minor contributor that is being queried, because for the same profile we calculated 3 different likelihood ratios, one with each contributor in turn being the queried one. So these symbols with the crosses in them correspond to the very low level 16 picogram contributors. I see now I'm mixing up measuring amounts of DNA with RFU and picograms. Sorry, I hadn't actually noticed that myself before. So down here, and now we do have a couple of cases where even though it is a true contributor, even with the peak height model, the likelihood ratio is slightly less than 1, so slightly negative on the log scale, but hardly anything, and we see some, more so for the discrete model. So down in this corner there is some improvement. Up here there is, that the peak height model is doing quite a bit better, but they're less interesting because these are the empty symbols here are for the ones with the higher amounts of DNA, and they're pretty easy to manually deconvolve anyway. So basically you're in the range where you can, the answer is so strong it doesn't really matter very much. So it's sort of interesting that these didn't reveal a huge advantage for the peak height model, but I think we're pretty convinced now from, I think others have shown, Keith and Peter Gill, I think showed some kind of similar kind of comparisons where there is enough advantage from the peak height model that I think that is probably worth using it. Yes?
I was just wondering, did you assume the the number of contributors to be known in these calculations?
Yeah, for these calculations, yes. I'll come back to that point in a moment. We don't always. Here's one. I won't go into too much detail, but this was a famous bra clasp in the Kircher murder case, which was a kind of very infamous case and a lot of attention. But the only point I want to draw here was this is one opportunity where we had a chance to compare with some other models, but also one of the big advantages of the peak height model is for the discrete model. There can be a lot of arguments about the near threshold peaks and whether they're stutter or not, and so there was in this case a lot of argument about classifying particular peaks, whether it was or wasn't stutter, and they were all working in this kind of discrete mode. And you see you can get hugely different answers. I won't go into details here, but basically those hugely different answers are about where you set the threshold and which peaks you classify as stutter and so on. So there were different in the trial, the original trial, they basically just dismissed every peak that wasn't consistent with the prosecution case, which is not a recommended strategy. So, so they got. I mean, it was really completely outrageous. Perfectly legitimate peaks were just dismissed because the defendant didn't have that allele, and so they got a huge overstatement. And then in the appeal, there was a sort of big reaction there and said all these low-level peaks have to be dismissed because they're not reliable. This was where I said, well, let's call all of those, instead of throwing them away, those low-level peaks, let's call them uncertain. So you get very different answers. But my point is really that with the peak height model, you don't have, all these things are modeled automatically. The stutter is modeled automatically, so you don't have to make any of these decisions anymore and argue over classification of whether it's stutter or not. And all the peak height models came up with a pretty closely the same answer there. So that I think that's probably more than the gain in likelihood ratio that I was showing you on previous slide. It's this kind of thing which is the advantage of the peak height model. So another thing that we took the opportunity to do was that there's some discrepancy around the world about whether it's worthwhile to routinely replicate DNA profiling. I think historically, particularly with low template DNA, in the early on, because it was sort of recognized to be so noisy, there was a sort of strategy of replication became kind of de rigueur in the UK and most of Europe. But one way or another, that wasn't the adopted policy in most of the rest of the world. So there are some arguments for and against. Replication is, on the one hand, the kind of cornerstone of science, and it can reassure courts and so on that we did it twice and we got some similar result. But ultimately, and it depends a little bit on the protocol, ultimately replication uses up some of your valuable resource, which is a low amount of DNA. Now, that's not always obvious in some protocols, because the way people do their DNA extraction is kind of a fixed protocol in many labs, and it generates an amount of liquid that allows multiple replication. So from that point of view, it looks like replication is for free and it doesn't use up the DNA, but really it always does. So what we're talking about here is a situation where you have a stain and it's got some DNA in it which you suspect to be low level, and you want to consider, okay, let's have a one-shot analysis of this versus splitting it up and therefore reducing an already low level of DNA in order to have the other benefits of replication. And is this a good idea? So what we've shown here is where we, in lab experiments, we kind of mimic this situation where you have two more, as far as we could do it, identical samples of DNA, and in one case we just did a single shot analysis, and in the other we split it into 2, 3, or 4, and then analyzed the replicates using our peak height model. And again, the y equals x is that the single replicate and the multiple replicates give the same answer, and just this x here is some mean for the equal contributors and for the unequal contributors. And broadly speaking, there seems to be on average no particular gain or loss, but that's pretty impressive in a way that the statistical analysis is efficient enough that even with that loss of information from splitting up into multiple replicates, the statistical analysis is able to recover basically all of that lost information, so that replication doesn't on average lose you any information. it may bring some intangible benefits in that, I mean, certainly if you go for a one-shot analysis, there is a risk, very small these days, that the profiling run will fail for some reason, and with replicates you've got some guarantee against that. So there are some arguments for and against, but probably given the cost, I think we'd guess that for most people the replication strategy isn't worthwhile. It is still routinely done in this country. There it is again with 3 contributors, again the equal contributors. I can't remember how we did this average, but it's some kind of mean. This X is bang on the line, and with the blue one for the unequal contributors it's also pretty close. So again, you can either see this as glass half full or glass half empty, that replication doesn't really it doesn't cost you anything in terms of loss of information, provided you've got an efficient statistical strategy from recovering. Clearly, if you divided further and further, all your profiling runs would eventually fail, and so at some limiting point, replication is a bad idea. But we didn't reach that in these experiments. We were pretty much able to recover all the information. Let's see. Okay, here's another interesting thing I think that I want to highlight a little bit, and this is when you've got a contributor of interest represented by a suspected contributor whose allelic peaks can be corresponding to the suspected contributor's alleles can be observed. The lower level contributors in some sense kind of don't matter and can be modeled as drop-in, and this is we think what this slide is trying to show. We think this is advantageous because there's often in a DNA profile some peaks that apparently correspond to the alleles of the contributor of interest, and there's often a lot of noisy other low-level peaks, and then people argue about how many contributors there are, and really that argument is completely irrelevant. Once you've got all the peaks of the contributor of interest at one point, no matter how many lower level peaks there are, it really doesn't make any difference to the weight of evidence. And so but people can get very hung up on this number of contributors. This is why I've said several times in the discussion that in a world where DNA contamination and degraded DNA is everywhere, then some low-level contamination is going to be present in every sample, and it really doesn't matter for the analysis, and therefore counting the number of contributors at some level doesn't matter, because you've got a sort of tailing off typically in the amount of DNA from each contributor, and so you're up to, there could be in a kind of dirty crime stain multiple contributors, but the amount of DNA from several of them is so low it doesn't matter. Now I'm jumping slightly ahead because I don't think what we show here really kind of fully validates this idea, but I'm just trying to encourage and say that it's a good idea. And so this is what we've done here. The blue again corresponds to 2 contributors, and the red to 3 contributors. So we analyzed this in the usual way, assuming 2 or 3 contributors as appropriate, and treating the others, one not the contributor of interest for the likelihood ratio. The other contributors are all treated as unknown. But for the two contributor case, here we just assumed 1 contributor and modeled the lower level peaks as drop-in. And for the 3 contributor case, we just assumed 2 contributors, and the middle contributor was the queried one, but the peaks corresponding to the lower level contributor were all just treated as drop-in. And then the 2 likelihood ratios are pretty much on the axis, saying you get pretty much the same answer, which, at least in this limited scenario, kind of validates this claim that the lower level contributors can all be treated as drop-in, and therefore it doesn't matter how many there are. I won't highlight this too much, but the linkage adjustment for relative calculations has been problematic for low template samples. There are kind of formulas for doing this for good quality profiles that have been around for a long while. So our idea was just to look at, for assuming taking the reference profile and comparing it with and without linkage. So linkage is when you have 2 loci on the same chromosomes. For unrelated people it doesn't matter, but for close relatives it can matter in the calculation. And so when you've got the full genotype of the individual, you can do a correct linkage adjustment allowing for the the relatedness being hypothesized. So for these calculations here, we've got a brother situation where the alternative is the brother of the suspected contributor. The linkage adjustment changes the likelihood ratio by 0.2 bands. What's conventionally done is to remove one of the pair of linked loci, and we're just showing here that there are two pairs of linked loci in the particular profile system we were looking at here. So there are 4 different ways of choosing 2 loci to remove, and that's quite an inefficient and noisy way of dealing with it. And our suggestion, which we've kind of verified in a limited way again, is that if you just take the fact that for the full profile, the linkage adjustment reduces the likelihood ratio by 0.2 bands, and then you just apply that correction to the likelihood ratio from the low template sample, so in other words just subtract off 0.2 bands, then that's a pretty conservative and fairly straightforward and simple way of doing a linkage adjustment. Alright, so there's introduction to our statistical model and some of the things that we've done with it. Most of it's published work done by my PhD student Christ Steele and with Matt Greenhalgh at Cellmark. Cellmark partly funded his PhD project, and so there's some of the things that we found that I've just been talking you through. I run out of time, and I had just a few other little things here, but I just do want to, because I did start 5 minutes late, so I can go a minute or two more, because this relates to the questions we had earlier in the week about with Bill's example about the prosecution and defense having different hypotheses. And this one, I remember Phil was an expert for the other side, and there are a couple of cases where he and I were experts for opposing sides, and we did written reports, but we never met in court. I'm sad to say that. I think that would have been interesting, but for one reason or another, we never opposed each other in court. But this is the sort of complexity that you sometimes get. G was the murdered individual, and D and M were suspected of the murder. So we were interested in, on this particular exhibit, whether there was DNA from D or M, but it was very low level and the likelihood ratios were quite low, and it mattered a lot whether you conditioned on G being present. Now, it's a fairly uncontroversial fact that G was present at the scene of his own murder, and so and therefore the presence of his DNA was unsurprising, but nevertheless you can't say a priori that his DNA was definitely present on this item, and it mattered a lot to the answer, because conditioning on G greatly increased, well, by order of magnitude or so, but there were pretty low likelihood ratio, so an order of magnitude mattered. So there was this preliminary decision about, can we condition on, are we justified in conditioning on G? And I tried to answer this question by saying, well, actually, we think D and M are present. That's the prosecution case, and you get this kind of circularity. In order to assess the evidence for D and M, you have to decide whether G is present, but to decide whether G is present, you have to know whether or not D or M are present, and there's no kind of good way around this, but it seemed like a fairly conservative assumption to assume that, and I think I did check this, that D and M were not present, and do this calculation, and came up with a likelihood of 100 million, and therefore in my report I said that the court may then wish to conclude that it's reasonable, since there's a strong prior implication, we knew that G was on the scene, and therefore a likelihood ratio of 100 million should be quite convincing that there is DNA present from G, and therefore we can condition on him when assessing the evidence against D and M. So it came back from the defense that, well, actually there are 7 interesting propositions that include G. I won't go through them in all detail. There was a question of 2 or 3 contributors, and then there were all these, and then for each of those there was D there and was M there and so on. So we came up with 7 interesting propositions, and then each of those had a non-G version, and so they asked me to report 49 likelihood ratios. And actually this is what I did at the time is kind of conflicting with what I was arguing for the other day, which is, when I remembered it, is kind of interesting that, and I think here, so I said, well, no, those 49 likelihood ratios would be kind of silly. They're all kind, likelihood ratios of individual hypotheses like that are just all over the place, confusing and so on. Ultimately, there's only one, basically you've got a probability of the evidence under one story versus the probability of the evidence under another story. And it was actually quite helpful that the defense narrowed attention to these 7 hypotheses and said these are the only 7 hypotheses that we're interested in, because then we could say, well, there's got to be some weighting up of the likelihoods for those 7 hypotheses under the proposal that G is present, and then under the proposal that D is present. So the prosecution had a specific hypothesis that the DNA came from G plus D plus M, and so it seems clear that the prosecution can make, whatever allegation it likes as long as it can prove it, but that's their right to propose that. And the defense, of course, doesn't have to specify any alternative, but here I said, well, we may as well, now we've got a limited pool of 7 alternatives, we may as well choose the one that's most favorable to the defense, which turned out to be this one. So the one which is gives the greatest likelihood without G being present, which is U plus D plus M. And then my working on this situation, so basically I said, well, the prosecution choose which of these 7 it likes, and the defense can choose which of these 7 it likes, and then let's take the ratio. And we ended up with 3 billion instead of 100 million. So it was even more convincing under this calculation. So the defense in raising this question had been kind of quite helpful in limiting the pool of hypotheses. Anyway, there was no further question on this, and we did go on assuming that G was a contributor. I think it's a sort of interesting question here, because you can't always, I think, allow both sides to specify whatever prior they like. I mean, in thinking, this actually goes back to another case where we had drop-in parameters, which I don't have anymore, but in one case the defense expert wanted to say, well, we don't know what the drop-in is, it could be really big, and if the drop-in parameter were really big, then conditional on that, the likelihood ratio is very low. And ultimately, by fiddling around with drop-in and drop-out parameters, you can make any evidence worthless, and it seems kind of clear that you can't allow the defense to put any prior. But here, it does seem like a reasonable thing to do. I don't really know in full generality. There does seem to be, taking it from a scientific perspective, if you look at some stain and you have some hypotheses about the contributors, knowing a particular allegation about who's the contributors shouldn't change your prior, but of course that's a kind of scientific viewpoint. It doesn't correspond to the sort of competitive environment of a court where there's competing situations. Anyway, that's what I did in one particular case. I think that's quite interesting. I've got some stuff on FST there, but I really have run out of time now, so I will stop there and give you some further bedtime reading. Oh, one last thing. I've got my book here, and I did bring a copy with me, and I don't plan to take it back. If anybody wants to have particularly any young researcher doesn't have a copy of my book and wants a free copy, I'm giving one away. And at the end of most of my recent talks, I've shown this slide, but this is probably the last chance I'll get to show it, because there's no point encouraging people to come anymore at this point. So thanks everybody.
Thank you very much. One question only, because there's plenty of opportunity, since this is the final session, for people to speak to David over lunch. Okay, we just one there, and that's
So often in the case when there is a perhaps reasonably assumed contributor, what we might do is actually do a likelihood ratio for that as the suspected contributor, and if it seems reasonably high, use that as a prior, then
that's essentially what I did, but it was contested by the defense in this case, because they could see, because I did report both.
Okay.
In my report I said, if it seems like there's evidence for this guy G to be there, if we condition on him being there, the likelihood ratio is this. But I did also report that if, on the other hand, if the court doesn't wish to condition on him being there, the likelihood ratio would be this lower value. But then I kind of argued that because there was this strong likelihood ratio for G being present,
Yeah.
that seemed reasonable, and that's what the defense seemed to be challenging with their query.
But did you do it separately? So
Yes.
Oh, okay.
Yeah. So
Okay,
I did a
okay.
separate calculation
Yeah,
for
yeah.
whether G is present and
Yeah.
ignoring
Okay.
D and M. That
all right.
the last question.
Yeah, so my point is on the difference between information in p-kites and just presence absence.
Yeah.
It's really difficult to make these sort of studies, right? Because you need to do something about the unknown parameters.
Yes.
And there you might actually end up introducing new information in the system, such as the penalized maximum likelihood. Take an extreme
Yes.
example. You take my favorite p-kite model, and it has some parameters, Now I make the discrete version of that model. I just say, see something about the threshold and not. I have the exact same parameters. In the first version, I have enough information in the system to actually do maximum likelihood. In the second, I cannot do maximum likelihood anymore, so I can't even get a likelihood ratio.
Yes, sorry, I'm not quite sure. There's a comment rather than a question. There's nothing. Yes.
To say what is the gain of using peak heights?
Yes, no, I agree. I mean, I take your
further
point. It's difficult because I don't think I need any persuading now. That when I only had a discrete model to offer, I kind of poo-pooed peak height models and said, "Oh, we don't really need them." But then when I had a peak height model, I immediately became convinced that this was better. But on the other hand, then I was a bit disappointed that our own experiments didn't really show up a huge improvement. And but personally, my own kind of subjective view is that I am convinced that there's enough improvement for it to be worthwhile and to be worth the extra cost in having to make all these additional assumptions, which are all, there's the usual problem with none of these assumptions is exactly true, but I think we've been able to verify them well enough that it's worth that cost to get that extra information. It's particularly those low-level ones where the discrete model gives you a negative log likelihood and a peak height model gives you a positive. They can be quite important in some
of course,
situations.
for any other question, here it's like the ratio focus, but if you actually wanted to know how much DNA is there for each person, it would be very difficult to get that estimate.
Yes.
Just a peak.
Yeah. So actually, that's another thing I didn't mention, that one of the things you can get out of these is an explicit estimate of the amount of DNA from each contributor, which, yes.
Thank you very much, David. And finally, to thank, on behalf of the organisers, all of the participants for coming and staying to the end, and have a safe journey home or continued presence in Cambridge. Thank you very much.